Alright, you guys, this is video E3.4-9 on earthquake-resistant structures. Please note or notice for these notes, on the left-hand side you'll see the actual PowerPoint presentation I'm running through, and on the right there's just some space for you to take some notes. So add anything extra that I might be talking about that you find important or interesting. For this, keep in mind, as you're taking these notes, of features that you may want or need to incorporate into a tower that you're going to have to build following earthquake-resistant design. Alrighty, so here we go. So earthquake-resistant structures. The problem with earthquakes is obviously it destroys our structures, but structure failures is what causes fatalities, not just the ground moving. The safest place to be, of course, during an earthquake would be outside in a place not near buildings. This is a picture of the 1995 earthquake in Japan, near Kobe, Japan, which is a port city in Japan. Killed over 1,300 people. Japan is a very, very, very crowded place. 1,300 people is a lot, but this is also a place that has built much of their infrastructure earthquake resistant. And you can still see the damage that this caused. This whole freeway was tipped over. I was in Kobe in the fall of 1998, and they were still rebuilding 3 years after that earthquake. In this picture, you guys might remember this one. In 2008, Sichuan quake in China claimed over 70,000 lives. This was a place in China where, obviously it was not a very wealthy province in China. The earthquake was an 8.0, so it was a very large earthquake. But you can see some of these structures. I guess you would say these structures are even very reminiscent of the more recent Haitian earthquake that claimed so many thousands of lives. But really, these structures were not built. They don't have the money to design and build structures to resist earthquakes. So for structural design, we stress earthquake resistant, not earthquake proof. We haven't figured out how to make something earthquake proof. I don't know if that's possible because you can't really predict an earthquake or its strength. And with that being said, it is certainly more expensive to build earthquake resistant. And so if we were to push towards earthquake proof, that may just not be a feasible option or a doable option because of how expensive it could be. So for design, buildings with foundations resting on unstable ground are more at risk because the ground can move more. If it's on the bedrock, it's actually much, much safer. The damage that a building suffers really depends on its displacement. Not on displacement, I'm sorry, but on acceleration of the ground as the different earthquake waves move through. In other words, how fast is that wave moving through? How fast is that energy trying to move through the building? Displacement is the actual distance the ground and building may move. Acceleration is a measure of how quickly they change speed as they move. So there's two ways to reduce the earthquake-induced forces on a building. One, it says increase the natural period of the structure, meaning we're talking about base isolation here. There's a base isolation system that we can add, and I guess I'll back up here in parentheses to say period, the time it takes for the buildings to make one complete vibration. So think of moving from one side to the other and back again. That would be one period of the wave, of that energy moving through it. Okay, if you can imagine that, the energy snaking through it. So we need to increase that, and we do this through a base isolation system, which we'll look at in a second. Number two, increase damping of the system by energy dissipating devices. In other words, devices that can absorb that energy as it's trying to move through. We'll also look at that. So base isolation. So the idea behind this is to isolate the building from the ground so that earthquake motions are not transmitted up through the building, or at least greatly reduced. In other words, we'll build this building on a big shock system, kind of like the shocks a car would sit on, to absorb the ground movement so the building itself isn't taking all that movement in. And seismic dampers. They're devices that we would add to a building to absorb energy It says much like shock absorbers in a car absorb um, the bumps or undulations of the road. So as we look at these three diagrams, we see one is stiffened. We see all this movement that's going to go on. Okay, shock and vibration sent into and contained within stiffened frame. For the bolted, stresses on cabinet frame and travel of shock and vibrations, and then the unbolted system, well, it's probably going to tip over. Okay. Base isolation system is going to allow this building to move independently, really, from the ground that would be around it. I have some even better diagrams to show you. So down at the bottom here, there's a great diagram. You'll see this in your research, this exact diagram. This base isolator system, lead rubber bearings. Okay, basically, it's a lead rubber bearing is made from layers of rubber sandwiched with layers of steel, and those act as the shocks that are absorbing that energy. And you see this moat. See right here, it says a moat around this system. So that this ground right here is going to move different than what this particular building will have to absorb. Okay. You also see some things here, cross bracing, that's pretty important. Something called a shear wall or the shear core down the middle also adds strength to that building. Actually, at this time, we're going to go ahead and I'm going to show you a quick video about a base isolator system.
चलते जाने
In that video that you just looked at, you saw that there were two different towers. One without a base isolator system, they had that little jar on top, and then the one with the base isolator system on the right-hand side. And it showed that building with that beaker on top moving a little bit more independently than the actual shake board that fellow on the right-hand side was moving. So you could see that some of that energy was absorbed, and that building did not have to, I guess, deal with or dissipate all of the energy from that earthquake. So the other thing we talked about was seismic dampers in the building. And you can see here are some different examples. It says a viscous damper. And this is kind of a piston system in a fluid. So that as that building moves, this piston will, as the building, I guess, flexes, can absorb and move up and down this damper. There is a friction damper. And then finally with these V-braces, yielding dampers. So seismic dampers will help as this building sort of, I guess, tweaks itself or moves side to side as energy is trying to move through it. They will lessen the amount of movement in the building. So right now I'm going to show you a quick video of some seismic dampers.